Now we're here. All right, let's see if you got it right. Let's see if you didn't miss a little layer. So the first thing was you needed to rewrite it as the tan of 3x squared plus 5x, all of it squared. So you got it. You have the 2 of all that to the first. Yes. Yes, you can. He's saying, can we just put all this like this? Yeah, that's fine. Keeping it clear. Look at that. How many people got all 3 layers? Yeah? That's not bad. Not one hand went up for people at home. Just kidding. Wow. What? All right, so any questions on that? Yeah, we love the chain rule. You did? Oh, yeah. You know what? And when I had to refilm that day, because I forgot to turn the sound on, I forgot to show the repick clip. I know, I know, I know. See, now it's all new for me. All right, let's check out this homework. Now, when you get to number 2, realize that I left it as is. I left the whole thing under the square root, so the whole thing was to the half. So that's what my answer looks like. If you broke it up, if you broke a number 2 up and you wrote it differently before you took the derivative, you might have a different answer. Like if you made it the square root of the numerator over the square root of the denominator, or you made a multiplication by multiplying to the negative 1/2 power, your answer is going to look different. But if you left it as is, that's what it's going to look like. And number 3, if you got the first part right and not the second part, you forgot the product rule for the derivative of x tan x. Oh, homework's in the book tonight. Yeah, we're going over homework. This was at 1 through 12? Did you get 1 right? Okay. 2, did you rewrite it first? Or did you just keep it all to the half, or did you rewrite it differently? Okay, so then you should have this. 1/2 of it to the negative 1/2. For derivative of the inside, you need a quotient rule. Yes? Yeah, I'll show you that. I'll show you number 2 separately in a minute. Yeah. Mm-hmm. What is d high? Nope. 1. That's why I didn't write it. But, times 1. Now, if you get down to 4 and you're like, oh, I got that wrong too, you might have a 12, and then it's times 2 at the end, right? Because you're the inside, and what's 12 times 2? You bring it in front. That's 24. You should. It's the right thing to do. Or you have to. That's an 11. So you have 12 times 2x plus 7 to the 11th times 2. But that 12 times 2, that's your 24. I just multiplied them together. When you get a couple constants and they're all multiplied in the answer, just bring them up front and multiply them. Same thing with number 5. If you don't have a negative 30 here, it's probably because you wrote it like this, your answer. But it's not wrong. It's just messy. All right? So if you got this, you got it right. I just didn't realize you could rewrite that. Can I go on to the next page? Are we looking? Okay, 6. I don't think there's anything weird about 6. 7, you probably didn't use your parentheses. You have to rewrite that tan squared theta as tan theta squared. So, because you might have forgot a layer in 7. You take the derivative of the sine of first, and that's cosine of tan squared theta. But realize, that's why you should write that as tan of theta squared. When you go to take the derivative of that, you have to take 2 tan theta to the first. That's the derivative of the second layer. And then finally, the derivative of the inside tan theta is secant squared. Theta, yes. Oh, yeah. You're very welcome. I'll just because it's to the side and I wanted you to see it. So 8 is the quotient rule. Approve of this. Wow. I guess we can continue then. Now, I know 11 and 12 were tough. A lot of people didn't have that on their papers or they weren't able to finish. So we'll make sure we go over that. And also, you wanted to see 2 done the other way. I know that. What's ugly? Which one? Okay, but 11, they rate the equation of the tangent line at the point 1, red 2. Oh, okay. Yeah, I definitely want to go over that. I mean, they gave you the x1 and the y1. All you had to do was get the derivative and plug in 1. Now, your slope might not look like this. I cleaned it up. So I'll show you what the derivative at 1 should be before you clean it up so you can see if you're right or not. Okay. Anybody still checking? Anyone still need to see anything, or have me say what it says? You can't read it. Okay, so for 2, Riley, you said you broke it up. You made it the square root of the numerator over the square root of the denominator. So then you write each with an exponent of a half. So you just go right into the quotient rule. So you have low, d high, less high, d low, all over. The denominator squared, well, it's to the half. So when you square it, it's just going to be to the first. Yeah, you like that better? So that was another way of doing number 2. This is just if you broke it up first. All right, we wanted to see, oh, yeah, somebody in the other class actually wrote it as a product first, but this one, my smartboard wasn't working right. They wrote it as multiplication times back to negative a half, and they used the product rule. Right? Who would do this? I don't. Yeah, I don't remember. Okay, this was 7, and again with 7, you couldn't leave this tan squared theta. You had to rewrite it as tan theta squared. Yes? Oh, it's actually better if you move any constant to the front. Yes, that is a better form. But yeah, with 7, a lot of people getting it wrong because they didn't rewrite this, and then you need parentheses around the whole angle for sine. So you have 3 layers. There, yes. Tan theta squared. Yeah, same thing. Yep. Okay, and the other one we want to talk about, so with 11, the whole thing that you had to get was the slope of the tangent, which was the derivative at 1. So to get the derivative, first you rewrite it, the function as x times 1 plus x squared to the half. And that's a product. So when you go to get the derivative, you have to use the product rule. Now, when you get this, you're going to have to plug 1 into it. So in this case, I thought it would be a good idea to simplify it. So if you look at this first term, you have, well, the half and the 2 cancel, but you have an x squared over the square root of 1 plus x squared, because this is to the negative a half. And the second term is just the square root of 1 plus x squared. When you actually have to plug numbers in, it's nice to rewrite it first, back in radical form. Now we have to plug in a 1 for all the x's. We want to know the slope of the tangent line when x equals 1. So you plug 1 into the first term, you have 1 over rad 2. If you plug 1 into you can go ahead. Plug 1 into the second term, you just have rad 2. So if you got for the slope of the tangent line 1 over rad 2 plus rad 2, you're absolutely right. Okay? I just wanted to combine them. I wanted to get them a common denominator. So I multiplied the second term by rad 2 over rad 2. So doing that, I got for the derivative at 1, 1 over rad 2 plus 2 over rad 2. That's 3 over rad 2. And if you want to go really crazy, rationalize the denominator by multiplying by rad 2 over rad 2. So yeah, that's the slope of the tangent. And that's where that came from. So I can scroll up if you want anywhere. Is anyone stuck anywhere? So you had to use the product rule. And then just plug in the 1. I rewrote it first, and I plugged in the 1, and that's what gave us. But everything else was all set, because they gave us the x1 and the y1. Now, I know the one you really want to see is number 12. 12 was fun, actually, because they wanted to know the derivative at -2, right? First, find the derivative. So y equals f of g of x. So how do you find the derivative of f of g of x? Yeah, you got to get the chain rule. Derivative of the outside function, f prime, evaluated at the inside function, so it's f prime of g of x, times the derivative of the inside function. You get the derivative first, and then you want to know what's the derivative when x is -2. Now, then you plug -2 in. So it's f prime of g of -2, and g of -2 is 5, times g prime of -2, which is 4. And then they tell you what f prime of 5 is. That's -7. So -7 times 4 is -28. Got it? So where'd you go wrong? Was it taking the derivative or just... Oh, okay. Oh, so all the kids who got 60, you did f prime of -2. But you had the g prime in, okay. Okay. Other questions? All right, let's see. How are your algebraic skills? How good are they? Oh, I didn't... I want you see this nice little equation here? I want you to solve for y. And I'll explain why in a minute, but I'll explain why. Okay. Solve for y. Get y all by itself. Xy minus y. This is plus y minus 4 equals 0. So it's x times y minus y times sine x. Hi. Y. Oh, actually, I didn't explain what explicit form is. I'm going to do that next. What explicit form is. Well, what's your first step? What are you guys doing first? Okay, you're on the right track. Move the 4 over. Let's see here. Xy minus y sine x plus y. You added 4 to both sides, that equals 4. Oh, great. Then what do you do next? Yes, Cameron. Factor out of y. That was great that you moved the only term here that didn't have a factor of y to the other side. So now y is a common factor. You can pull it out. And when you pull out a common factor, you just... Oh, yeah, but then how do you figure out what the other factor is when you pull out the y? You need something? Ryan. You sure? Okay. All right, so the other factor you get by dividing through by whatever you pulled out. So what goes in here? Plus 1. And now we can finally solve for y. What do we do to solve for y? Divide. Okay, I had to make sure you had those skills. Oh, come on. You get that, right? Here's the thing. When I first gave you the function, it was defined implicitly with an M, okay? X's and Y's were all kind of mixed up. When you solve for Y, when you get Y all by itself, now it's defined explicitly. And so you see the difference? Here's a function up here defined explicitly. That's what we're usually given, Y equals. On the other side, no Y's. But today, we're going to work with functions that are defined implicitly. We're going to learn how to find the derivative, how to find dy dx of a function defined implicitly. And this is called implicit differentiation. You're finding the derivative of an implicitly defined function. So what you guys just did was you took this implicitly defined function and you defined it explicitly. You got y equals. See, now if you had to get the derivative, you could just get dy dx equals and use your quotient rule, right? Yeah, but you know what? In reality, you're not going to be able to solve for y. You're not going to be able to rewrite your function explicitly and then just get the derivative the good old-fashioned normal way. Just algebraically, it won't be possible. But this time it was. But yet you still want to know what that derivative is, right? Right? Yes, yes. We don't care what we have to do to get it. We want that derivative. We want dy dx. Do we agree? Yes, okay. Before I have the steps here, and we're going to go through this. These are the steps to find the derivative implicitly. But I have to make sure we're clear on something that gets a lot of people. Yeah, hopefully it's going to clear things up. When you find, I have it here, but it's written sideways. When you find the derivative, oh, it's starting, and I am recording. When you find the derivative of y, oh, when you find the derivative of y with respect to x, that is dy dx, right? Think about what you've always done. Like if you had y equals x squared and you took the derivative of y with respect to x is dy dx, and then it would be 2x, right? You've been saying it all along. So the derivative of y with respect to x is dy dx. But, if you take the derivative of, is this even going to work? I'll do it over here. I think I'm better over here. If you take the derivative of x with respect to x, dx dx, what is anything over itself? 1. So the derivative of x is 1. The derivative of y is dy dx. You got that? So if it's just x, the derivative is 1. You don't have to say 1 dx dx. You just say 1. Okay? But when you take the derivative of y with respect to x, it's dy dx. So when you want to take the derivative of a power of y, like y squared, I want you to just think of the chain rule. Chain rule says, well, first you take the derivative of the outer function. So something squared. What's the derivative of y squared, do you think? 2y to the first, right? That would be the outer function. But then times the derivative of the inside. What's the derivative of y? 1 dy dx, right? It's dy dx. So the derivative of y squared is 2y, or because of the chain rule, times dy dx. If it was x squared, just 2x times 1, you just say 2x, right? So the derivative of x squared is 2x. You don't have to say dx dx. So if I say what's the derivative of x squared, that's just 2x. You don't have to say dx dx. So if it's an x, you don't worry about it. What about, I thought I had a y cubed on here somewhere. What do you think the derivative of y cubed is going to be? 3y squared times dy dx. Because when you're thinking of this as a chain, y is equal to something in terms of x. It's some function of x. You don't know what it is, okay? Maybe it's the sine of x. Maybe it's x squared plus 3. Yes, of the inside, which is the derivative of y. What's that? It's just the chain rule. It's just that you have to know that the derivative of y is, it's like saying the derivative of y with respect to x is the derivative of y with respect to x. Yeah, well, yeah. Okay. So just, that's the only thing. Everything else now is easy if you can get that. What's the derivative of x cubed? 3x squared. But y cubed, it's dy dx. Okay? So anytime you take the derivative of y, don't forget your dy dx. You don't need it. You don't need to write dx dx. All right, here we go. We're trying to do this. So I said we have some steps. And you know what? I'm sorry. The first one is so boring. I just have to just eliminate it. No, we're going to go to, because I want to get to a harder one. The second one is, B is so easy, trust me. I just said the first one. Wouldn't you just get y by itself and then just get dy dx that way? I don't know. I mean, this one, at least, it's worth your while to do this. Yeah. Okay, the first step to find the derivative implicitly is to take the derivative of both sides. Okay? And you're going to obey all your rules. So the left side is a sum. So how do you find the derivative of a sum? Individually. What's the derivative of y squared? Aha, they remembered. 2y dy dx plus, now I have to take the derivative of 3y. Now that's a constant multiplier, so that can just hang out. So it's 3 times what the derivative of y is, dy dx. It's 3 times the derivative of y. The derivative of y is dy dx. That's the one thing you got to remember. It's not just, derivative of x is 1. The derivative of y is dy dx. All right, and then it has to equal the derivative of the other side, 1. So your first step is you take the derivative of both sides. Now, you don't have to distribute here, but if there was any distributing to do, you would do it. Now, you want all the dy dx terms on the left. Well, they're already on the left. You see that? Just like, remember when you did that problem a minute ago? You got all your y's on the left and you moved the 4 over. Okay? You have only dy dx terms on the left, so what can you do? Pull it out, right? That's why I had you do that, so you would see, okay, so that means we can factor it out. And then you're almost there. I wrote doesn't apply here. This doesn't apply was supposed to be on the step 3. So what's in the parentheses? Y plus 3. And finally, we can solve for dy dx by dividing. So we divide both sides by 2y plus 3. We have the derivative equals 1 over 2y plus 3. It's fun, right? And in the past, every time you got a derivative, it was only in terms of x's, a little bit. And so you would plug the x coordinate of a point in there. Now, like, if you want to know the slope of the tangent line to this graph somewhere, you're going to need to know the y coordinate of the point. What? Because there's a y there. Oh, we'll see it. Next one. Oh, where? Because when you have to, when you're taking the derivative with respect to x, okay? So every term, like if I put a d in front of every term, I'm saying take the derivative. Whoa. Okay. When you take the derivative of x with respect to x, that is dx over dx. That's just 1. Okay? But when you take the derivative of y with respect to x, dy over dx is not 1. That's the derivative. That is dy dx. And then the derivative of any constant is 0. You can't even see that over there. All right, here's a really fun example. Does anyone know what the graph xy equals 4 looks like? Like when x goes up, y would go down, right? Like an inverse variation kind of thing. You've probably seen something like that. It looks like that. Kind of. Right, because the product is always 4. So we want to know what is the slope of the tangent. What's the derivative when x equals 1? I know this isn't a great graph, But at x equals 1, the slope of the tangent, you think it's going to be positive or negative? Oh, it's negative. All right, now let's actually find it. Let's use implicit differentiation. So we're starting out with x times y equals 4. The first thing you have to do is take the derivative of both sides. To take the derivative of the left side, what am I going to need to use? Product rule. All right, let's try this. First, x. All right, I want to hear it. What's the derivative of the second? Plus the second, y, times the derivative of the first is 1. Good. Equals the derivative of 4, 0. Okay. So we took the derivative of both sides. Now there's nothing to distribute, so we want only dy dx terms on the left. Okay. So what should you do next if you want all your dy dx terms on the left? Yes. Subtract y from both sides. So we have x dy dx equals negative y. Now we don't even have to pull out a dy dx, it's only in one term. So now we can just divide. So the derivative of this function is equal to negative y over x. Now we weren't just asked for the derivative, we were asked for the derivative dy dx. We want it evaluated when x is 1, but I need to know the y coordinate too. If x is 1, and it's a point on the graph xy equals 4, what does the y coordinate have to be? 4. Do you see that? That's the point 1, 4, because x times y has to equal 4. So at this point, 1, 4, what is the slope of the tangent? Well, it's negative y over x. So negative 4 over 1 is negative 4. We needed both the x and the y. So to get the y coordinate, we had to go back to the original, to get the y coordinate of the point. Cool. You love it. I want to show you one where you're going to have to distribute, because it doesn't get any harder than this, and it's on the AP exam every single, this is like a definite question on the AP exam, implicit, find the derivative using implicit differentiation. So I want to do the most exciting looking one here. Did I put F on yours? Yes. It's awesome. Because this one, whenever y is inside another function, you're going to have to distribute. And that's as hard as it gets. So we're going to have to take the derivative of both sides. Chain rule. All right, let's start taking derivative of the left. What do we got? Cosine of, oh no, cosine of xy. I might have to start a little lower. It might work better down here. Okay, it's better here. Cosine of xy. We're not done with taking the derivative, because with times the derivative of the inside, what do we need to use? Product rule. Whoa. Okay, so here we go. First, x times the derivative of the second, dy dx, plus the second y times derivative of the first, 1. We can write it. Okay, that's the derivative of the left-hand side. That has to equal the derivative of the right side, 6x. Now, before you can move all of your, when you move things, you're subtracting or adding. You can't do that until you multiply. So you see we're multiplying. We can't just subtract this, because we got to multiply first. You need to distribute first. This doesn't happen often. It only happens when y is inside. So if we distribute the cosine xy, we have cosine xy times x dy dx plus cosine of xy times y equals 6x. We just had two terms, right? You're distributing a times b plus c, right? Just this. Now you can get that you can move things by adding or subtracting. You just have to do multiplication first with PEMDAS. So now we want only dy dx terms on the left. So what do? Yeah, first you got to subtract. we're going to subtract the cosine xy times y from both sides. So we have cosine of xy times x dy dx equals 6x minus cosine of xy times y. Now our dy dx terms on the left, we only have one of them, so we don't have to even factor it out. We got one more step. Divide, right? To solve for dy dx, we're going to divide both sides by cosine of xy times x. Oh, can I cancel that cosine xy? I see things are the same. Oh, yeah, no. Because that cosine of xy is not a factor of the entire numerator. It's only a factor of one of the terms in the numerator. So that's your answer. How's that for a derivative? So fun, right? Really? Ashley Hawkins loves implicit differentiation. Okay. So basically, if you had to list a few steps, what's the first thing you do if you have to get the derivative implicitly? Take the derivative of both sides. Take the derivative, I'm not even writing the, that's how crazy I am. Derivative of both sides. Obeying all the rules. Okay, then after you take the derivative, you have to distribute if necessary. All right, you can always go back and fill this in. I'll finish, but you have it there somewhere. If necessary, then you move all the dy dx terms to the left.
Serena Fox to guidance, please. Serena Fox, please come to guidance.
Make sure you got the, if you need to take a picture of the book, it's open to it. It's 1 to 19 odd. It's open right there on the side. On the left. And you can factor out the dy dx. And then you can solve for dy dx by dividing. Yes.
Oh, never mind. My calculator wasn't working at first, and now it is.
See, that's like my smart board. When somebody looks, it works. But when I'm by myself struggling, oh. All right, and that's the end of our implicit differentiation.